Welcome. So in this video, we will learn about various methods to detect foreign fats, oils in ghee. Various methods which are there, which have been developed to detect foreign fats in ghee that we will detect, that we will learn in this video. So first, what do you mean by adulteration? So adulteration means addition or removal of anything from the genuine food product in order to make profit. Addition or removal of anything from the genuine food product in order to make profit, extra profit, that is known as adulteration. Now, as per FSSAI, adulterant is any substance which is added to the food for the purpose of adulteration. Now, adulteration in milk and milk products is very alarming stage, is very critical stage. Holy foods are not spared, even holy foods are not spared. Adulterators, in order to earn money, they are also adulterating the holy foods. Humanity is at the back seat, so there is no humanity. Every purpose is to mint money, every purpose is to make profits. And adulterators are smarter than us. So here we develop a method to detect any adulterant in ghee, and they are ready with the new adulterant for its addition in ghee. So that way the adulterators are very smarter than us. So only solution is that we have to follow a proactive approach. So we have to be proactive in this regard. We have to develop a robust method, full method, so that we can detect adulteration of different foreign fats in ghee. Okay, now coming to ghee. Ghee, as we know, is a popular traditional dairy product of Indian subcontinent, and more than 30% of the milk produced in India is converted to ghee. So more than 30% of the milk that is produced in India is converted into ghee. Now, importance of ghee is need not to be emphasized. It is a good source of fat soluble vitamins, good source of essential fatty acid. It is used as base material for the preparation of many unami and Ayurvedic medicines. It is used as a base material for the preparation of many umami and Ayurvedic medicines. It is known to boost memory, and short chain fatty acid present in ghee are having better digestibility and are having carcinogenic properties. So there are so many benefits, but sometimes, especially in lean season, its supply decreases and it becomes prone to adulteration by unscrupulous traders in the market. So here we can see that ghee, as per FSI, is defined as the ghee means the pure clarified fat derived solely from milk or curd or from desi butter or cream to which no coloring matter or preservative has been added. There should not be addition of any coloring matter or preservative in ghee. So ghee means pure clarified fat derived solely from milk or curd or from desi butter or cream to which no coloring matter or preservative has been added. Now, ghee market in India size reached around 2,907 billion rupees in 2022. So as per recent reports, we can see that the market of ghee in India is increasing. Around 30% of the milk produced in India is converted into ghee. So as already told, that around 30% of the milk produced in India is converted into ghee. So it is second most consumed product after the milk. And ghee is used for the preparation of many Ayurvedic medicines, and is reported to boost memory. It is also reported to boost memory. It is a rich source of fat soluble vitamins A, D, K, and also essential fatty acids and CLA, that is conjugated linoleic acid, which possesses the anti-carcinogenic properties. Now in ghee, if you see the ratio of omega-6 to omega-3 fatty acids is around 2.3, which is appropriate, which is proper for the neuronal development and also to prevent most chronic disorders. So in ghee, ratio of omega-6 to omega-3 fatty acid is around 2.3, which is appropriate for proper neuronal development and also to prevent chronic disorders. Now, ghee is the costliest fat with price about 4 to 5 times higher amongst all other fats and oil, and thus making it very prone to adulteration. So its cost is very expensive product, and its lean season supply decreases, so it become prone to adulteration by the unscrupulous traders in the market. Now, physical texture of oils and fats resemble with that of the ghee, and their addition in ghee cannot be detected by visual examination. So their physical texture, we see the oil and fat, if we are adding into ghee, they cannot be examined using the visual examination. So some methods have to be developed for detecting them. So here we can see that some of the news imprints. So regularly we are reading in the newspapers, in the media, in the electronic media, that ghee is being adulterated in different parts of the country, as we can see from the slide. So regularly the news are coming up. So this is very much necessary to detect methods to detect adulteration in ghee, and those methods will be covering some of the methods which have been developed and some of the methods which are really effective to detect adulteration in ghee, that we'll be discussing in this video. So I was telling you that some in lean season supply of ghee decreases and it becomes prone to adulteration by unscrupulous traders in the market. So what type of adulterants they are adding? It may be animal body fat. They can add animal body fat in ghee, vegetable oils in ghee, hydrogenated oil or fats, mineral oils, or mixture of these can be added into the ghee. Now recent studies show that around 23% of the market ghee sample failed to meet the FSSAI standards. So the adulteration in ghee is a very alarming stage. Now we will see some of the methods to detect adulteration in ghee. So some of the old methods also we'll see, and then we will switch on to some of the latest development which have been made to detect adulteration in ghee. So first point is the melting point. Now melting point of milk. So we know that ghee is having variable composition of triglyceride in it, so it is not having uniform melting point. It is having a range, broad range, because of the variable composition of the triglycerides present in it. It is having broad melting range, that is melting point of milk fat ranges from 28 to 41 degrees Celsius. Now vegetable oil obviously have lower melting point, as can be seen 20 to 30 degrees Celsius, whereas body fat is having higher melting point ranging from 36 to 51.3 degrees Celsius. So by this method adulteration less than 20% is not possible. Detection of adulteration of vegetable oil and body fat in ghee less than 20% is not possible because because of the presence of variable composition of the triglyceride present in it, because obviously the range is there in the milk fat range. So again repeating that ghee is not having a sharp melting point. It is having a variable melting range that is ranging from 28 to 41 degrees Celsius because of the presence of variable composition of triglycerides present in it. And vegetable oil is having melting point ranging from 30 degrees Celsius, and body fat is having 36 to 51 degrees Celsius. So adulteration of less than 20%, if they are adding to less than 20% in ghee, then these are not detectable by using this method, melting point method. Then another term is, which is another test, is apparent solidification test. Apparent solidification time test we used to call it. So that the name indicated another time required for a melted ghee sample to apparently get solidified at 18 degrees Celsius. Okay, this is the definition. So it is defined as the time taken for a melted ghee sample to apparently get solidified at 18 degrees Celsius. So it was initially developed by Kumar et al. 2009, and it was determined by taking 3 grams of the melted fat sample in a test tube, which we see for observed apparently solidification by solidified at 18 degrees Celsius. At 18 degrees Celsius, how much time is taken by the melted fat sample, 3 grams of melted sample, to get apparently solidified? For example, for milk fat, it takes apparent ASTs, that is 2 minutes 1 second to 3 minutes 5 seconds. Whereas for cow milk fat, cow ghee, it is ranging from 310 to 375. Whereas for animal body, because obviously it will be taking less time to get solidified, it's less than 1 minute. So again, in this, by using this method, adulteration, if they're at the lower than 10%, that is not detectable. So method can be detect the adulteration of milk fat with animal body fat at levels of greater than 10%. Okay, so animal body fat can be detected using this test at a level greater than 10%. So apparent solidification time test is, the name indicated, defined as the time taken by the melted sample, that is 3 grams of the ghee melted sample, to apparently get solidified at 18 degrees Celsius. How much time it is taking? So obviously animal body fat are there, they will take less time to get solidified. Vegetable oil are there, they're already liquid form, so their apparent solidification time will be much lower. And then if you want to detect animal body fat in ghee, that is possible only at a level higher than 10% level. Then another that is complete liquefaction time. This is just opposite of the AST. So the name indicated the time taken by the solidified. If we have first we solidify the fat sample, and then to get completely melted at 45 degrees Celsius. So 45 degrees Celsius, how much time is taken by a solidified fat sample to get completely liquefied at 45 degrees Celsius? That is known as the complete liquefaction time. So you take molten fat in a test tube, and it will be at 60 degrees Celsius. Then you keep the test tube at 5 to 8 degrees Celsius for solidification in a refrigerator, and then you take out the test tubes and then place it in a water bath, say at 45 degrees Celsius, and then you note the time for the complete melting of the fat. So here we can see the pure ghee takes around 2 minutes to 12 seconds to 3 minutes 15 seconds. Buffalo and goat body fats, they take 3 minutes 31 seconds to 3 minutes 48 seconds, and pig body fat it takes 3 minutes 23 seconds to 3 minutes 25 seconds to completely get liquefied. Okay, then again from this test, adulteration less than 10% is not possible. For pig body fat greater than 15% level only is detectable. For buffalo and goat body fat, 10% level we can detect using this test. This is a complete liquefaction time. That is again repeating that the time taken by solidified fat samples to get completely melted or completely liquefied fat 45 degrees Celsius, that is known as the complete liquefaction time. Then the fourth test is the Boehmer value. So Boehmer value is equal to the Tg plus twice of Tg minus Tf. Tg plus twice of Tg minus Tf is nothing but the Boehmer value. Tg is the melting point of the saturated triglyceride. Okay, so what is Tf is the melting point of the fatty acid obtained after the sonification of these triglyceride. Okay, so Tg is the melting point of the saturated triglyceride, and Tf is the melting point of the fatty acid obtained after the sonification of these triglycerides. So Boehmer value is equal to Tg plus twice of Tg minus Tf, sum of the melting point of the saturated triglycerides and twice the difference between the melting point and that of the fatty acid obtained after the sonification of these triglycerides. So ghee is having Boehmer value ranging from 63 to 64, whereas body fat is having Boehmer value ranging from 68 to 69 for goat, sheep and buffalo fats, and for pig body fat is ranges from 75 to 76. So increases after the addition of body fat in ghee even in the presence of vegetable oil. So in this, by using this test, we can detect body fats and vanaspati greater than 20% level, but if they are added at a lower level less than 20% level, so this test is not useful. Okay, so again repeating, what do you mean by Boehmer level? Boehmer value is equal to Tg plus twice of Tg minus Tf. Tg is the melting point of the triglyceride, saturated triglyceride, and Tf is the saturated and melting point of the saturated fatty acids obtained after the sonification of these triglyceride. And using this test, adulteration less than 20% is not detectable for the body fats and the vanaspati ghee. Then comes the opacity test. So opacity test is same as the AST test. Only thing that we have made the test as subjective. In this, the test has been based as objective, because in AST we were making use of we are visualizing the solidification point, but here in this we will measure the absorbance and then we will make the result objective. So time required of fat sample at 23 degrees Celsius to acquire absorbance in the range of 0.14 to 0.16 and conjugate transmittance of 68 to 78%, showing onset of the solidification of fat. That is known as the opacity test, and it can be used to detect dilatation of ghee with the animal body fat. So here we can see that dilatation at 10% level, greater than 10% level is not possible. That is possible. Less than 20% is not possible. So pure ghee is having opacity time of 14 to 15 minutes, and ghee related with animal body fat is having opacity time of 2 to 9 minutes. Obviously, because animal body fat will get solidified very faster, and the ghee related with vegetable oils will have more AST. That is because it will take more time to solidify. So 21 to 25 minutes is the solidification time, that is opacity time for ghee added with vegetable oils. So adulteration parameter which are based on physicochemical constants. So these which have shown in the FSI standard also, that RM value for milk fat it should be minimum 24 in ghee, whereas body fat it is less than 1, and for vegetable oils it is less than 1 again, because RM value is indicative of the source chain fatty acid like butyric acid and caproic acid. So for body fats and vegetable oils, their value is less than 1. Bronsky value, that for ghee it ranges from 0.5 to 2, and for body fats and vegetables these are less than 1. Then sonification value, if you see, that is milk fat for ranges from 205 to 235. It ranges from 205 to 235, and obviously for body fats and vegetable oils will have lower values, that is 192 to 203 for body fats and 170 to 197 for vegetables. This means that if we are adulterating the ghee with the animal wood fats or vegetables, then sonification value decreases. And add value ranges from 25 to 38 for milk fat, and for body fat ranges from 36 to 49, and then in vegetables again it is 74 to 145. Now BR reading as per PSI, that ranging from 40 to 44, whereas for body fat it is ranging from 44 to 51, and then for greater than 50 is there for the vegetables. So these are the physicochemical constant, which means that these are constants for ghee. And then if we are observing deviation, and if the mixture, the problem with this test is that although to some extent vegetable oils and the animal wood fats are individually are able to be detected at level, but when they are added in their mixture, it becomes very difficult to detect them, because that animal will have these values in one direction, whereas the vegetable oil will have the values in the opposite direction. So when these are added in a ratio, that makes the adulteration possible, and then the values falls within the range of the fat value, that is the physicochemical constant for the fat. Okay, so in this we can see that tallow, refined cotton seed, hydrogenated oil, coconut oil cannot be detected to a lower level less than 10%, and detection of adulteration in cow, ghee, vegetable or vanaspati or body fat added individually or in combination at 10% level or higher is possible, and it is failed to detect body fat that is at greater than level 10%. So the meaning that at level less than 10% is not detectable for vegetable oils in this for different physicochemical constants. And if you are adding vegetables, that RM value, if we are adding body fats and vegetables in milk fat, then obviously RM value will decrease, Bronsky value will decrease, sonification value will decrease, iodine value will depend on the type of animal vegetables. Again, BR reading is there, that is also if we are adding both, then it becomes problematic, because it is added in a way, the adulterators and unscrupulous people, they are adding in a way to maintain the ratio of the saturation and unsaturation in ghee. So we know that the ratio of saturation levels to the unsaturation level in ghee is 70 to 30%. So they will add animal body fat and the vegetable oil mostly in the ratio 1:3, so that their value of physicochemical constant falls in the range that is there for the ghee. So coming to BR reading first. So BR reading has already told that for milk fat it ranges from 40 to 44, and then for vegetable oils is greater than 50. Coconut and palm oil ranges from 35 to 40. Okay, because it is lower than the ghee also, so this is the exception. So these two fats are also called the problematic fats. So then body fats we have the 40 to 46, and then cow and pig body fat ranging from 47 to 51. So here we can see that different types of adulteration are there, but never less than 10% of the vanaspati or mustard oil that can be detected. Coconut oil cannot be detected at a level lower than 20%. Pig body fat again it cannot be detected in 20% in cow ghee less than, but not at all in buffalo ghee. So these are the different studies which have been carried out, but altogether saying that physicochemical constant offers advantage only to a small extent. If the adulteration is there at a level lower than 10%, then these physicochemical constants are not that much useful to detect the adulteration of vegetable oils and body fat in ghee. Then we have a dual purpose milk butarometer also. So sometimes milk, that vegetable oil has been added to the milk, that also can be detected using the dual purpose butarometer. So we know this is a normal butarometer and this is a modified butarometer. The modified butarometer opens at both ends. So top at the bottom opening is there at the both ends, and then we can simultaneously determine the quantity as well as the quality of the fat. So if the way we are determining the fat content for milk in in butarometer, that can be done by this butarometer also. So that way we can depend the quantity, and then we can, after that fat has been obtained, we can extract using a syringe from the up top part here. From this part, this cork will be removed, and then we can take the fat from using a syringe, and then we will place it in a refractometer and note the BR reading. Then simple and rapid testing for milk fat purity using BR reading of the isolated fat at 50 degrees Celsius using corrected formula. So in this we have whatever BR reading that is observed, that has to be multiplied by 1.08 to have the corrected BR reading. So this test can be applied at the reception dose also for accepting or rejecting the milk, and the method has been noted by BIS. Okay, so that the test is applicable at reception dose for accepting or rejecting the milk. Now in this fat which is isolated from milk by Gerber method is checked for the BR reading, and the correction factor, as I told you, that we have to apply the whatever value is obtained by 1.08, and this factor is to be applied because there occur hydrolysis of the fat by the concentrated H2SO4. So that way we have to apply this correction factor also, that is 1.08. And in this we can detect 10% vegetables. Detection is possible except the palm oil and the coconut oil. So except palm oil and coconut oil, we can detect other oils in milk using this test, and if the adulteration is a level lower than 10%, that is not detectable. So this correction, again repeating, this correction factor is because of the hydrolytic effect of the Gerber's sulfuric acid on the fat. So that's why the BR reading is to be whatever BR reading you are observing, that has to be multiplied by 1.08 to have the corrected BR reading. And by this test, the adulteration less than 10% level of vegetable oils is not detectable. Then there is another test which is called as the modified Weber test. So this is also a test. In this we are using a color developing agent, which is the water H2SO4 and HNO3 in the ratio 20:6:14. So in this ratio we will prepare the solution, and then we will take 1 ml of the sample in the test tube. Then we add 1 ml of the hexone, and then 1 ml of this reagent, which is the modified Weber reagent. And then if we are appearing the yellow brownish tank is there as shown on the slide, then we will say that the ghee is adulterated with the vegetable oil. So in this the adulteration level that 5%, 5 to 7%, 5% is observable. So we say that if the vegetable oil has been detected, that is adulterated in ghee, the vegetable has been adulterated in ghee, that can be detected by using the modified Weber test. So 5% detection of vegetable oil in ghee is possible by using modified Weber test. This the solvent used is hexane, and the reagent which we are making uses a mixture of water H2SO4 and HNO3 in the ratio of 20:6:14. Then another test is there to detect the holiday test. I told that mineral oil can also be added, even non-edible mineral oil can be also added in ghee by the unscrupulous traders, all traders, in order to make profit. So as we know that mineral oil, when added into ghee, if we are spoonifying that ghee, mineral oil is not at all spoonifiable. So if we are adding water after spoonification, then if turbidity is appearing, then we will say that mineral oil has been added into the ghee. So in this we will take 1 gram of fat, and 1 gram of fat. This video is already there in this channel, you can watch it. In this 1 gram of fat is taken, and then we add 25.4 ml alcoholic KOH in a round bottom flask, and then you spoonify for 1 hour. And then after that you add 10 ml of hot water, and if turbidity is there, then mineral oil is present in it. Appearance of turbidity, because mineral oil are not sponifiable. So if you are adding after sponification, water is there being added, then there will be turbidity will be appear, and if it is pure sample, then this appearance of turbidity won't be there. Then GLC of fatty acids, that we will see in a while also, that but already told you milk fat is having short chain fatty acid which are devoid in animal wood fat and the vegetable oils. Body fats are having higher of palmitic acid, stearic acid, oleic acid. Vegetables are having higher of palmitic acid, stearic acid, oleic acid and linoleic acid, whereas in coconut oil we are having lauric acid and myristic acid to higher levels. So if any change in composition is there, that way we can detect the adulteration. Say if the short chain and medium chain fatty acid decreased, if we are adding body fats and vanaspati, and then 20% level is detectable. Some marker fatty acids are there, for example erucic acid is there in the erucic, that the rapeseed oil. So if this is coming in your fatty acid composition, then obviously that it is present, and we can to a level of 5%. Linoleic acid increases. Some researchers have also used these ratios: C16 is to 14, C18 1 is to 18, and C18 is to C14 by arriving at these ratio. And if we are finding that this is the ratio which are to be there for milk fat in that range if not being obtained, then we will say that body fats, that is 10% body fats and vegetables, are detectable by this method. So if a higher percentage of them are there, that was not detectable. Then there is a test for cottonseed oil also. So we know that in cottonseed oil we have cyclopropanic acid, that is malvolic, and the sterculic acid. We have malvolic acid and the sterculic acid in cottonseed oil, and there are two tests by which the cottonseed adulteration in ghee can be detected. One is the Halpern test. Halpern test is based on the principle that cyclopropanic acid reacts with the Halpern reagent. Halpern reagent is nothing but the 1% sulfur solution in carbon disulfide is to isoamyl alcohol, that is in the 1:1 ratio. So you prepare 1% sulfur solution in carbon disulfide, and then you prepare isoamyl alcohol is there, then you mix them both of them in 1:1 ratio. That will be the Halpern reagent. And this cyclopropanic acid which are present in cottonseed oil, they react with the Halpern reaction to give the crimson color. This is the principle for this test. So how to perform it? You take 5 ml of multi-fat in a test tube, and then equal amount of you add 1% of the sulfur solution and 1% carbon dioxide along with the equal amount of the isoamyl alcohol was added to the test tube. Okay, so 5 ml of the Halpern reagent, 5 ml of the melted sample you take in a test tube, and then the content was mixed thoroughly and placed in a saturated. Here saturated brine bath we have to take that because we have to increase the temperature to 110 to 115 degrees for 90 minutes, and we will see that the crimson layer will crimson red color will observed in the case of the cottonseed adulterated sample. Okay, so this is the basic principle. Halpern test is used to detect the cottonseed oil in ghee, and then in this we are making use of Halpern reagent, which is nothing but the 1% sulfur solution in carbon disulfide is to isoamyl alcohol ratio 1:1, and then if we take 5 of the multi sample and 5 of the Halpern reagent, and then we keep the test tube in a saturated white brine bath, maintain at 110 degrees Celsius for 115 degrees Celsius for 90 minutes. Then we the crimson red color will appear. Then we say that cottonseed oil is present in it. Then another test which is used to detect cottonseed oil in ghee is the cyclopropanic acid. So these cyclopropanic acids have tendency to reduce the methylene blue. So if cottonseed oil is adulterated, then we will see that the MBRT, that is the reduction of methylene blue, will be faster. That decoloration of the methylene blue will take place if the cottonseed oil is there in the case of ghee. But then, since if pure ghee will be there, then decoloration of methylene blue will be there. So this way there are two tests which can be used to detect the adulteration of cottonseed oil in ghee. One is the Halpern test, other is the MBRT test. Then we can go for microscopic examination also. So this is a test. In this test, what is there is that we are isolating the sterol from the sample. So whatever sample is there, so we will isolate the sterols, and then we will observe under the microscope. So for cholesterol we will have the crystals which are obtained that will be obtained under the microscope. So for cholesterol we will have the parallelogram like structure of the cholesterol, that is axial angle that will be 100 degrees. So there we can see that like this is the structure of the cholesterol crystals, and then we have the phytosterols, that is a 108 degree angle will be there. So they will be hexagonally shaped like this. So axial angle will be 108 degrees Celsius for pure phytosterols. But when the mixture will be there, that is vegetable oil has been added into it, then the cluster will have the swallowtail re-entry angle will be there. So you can see that there are re-entry angles that have been followed. The structure will be like this. So if that the vegetable oils have been added into the ghee, and then we are isolating the sterols and observing the crystal under the microscope, the adulterated samples will show this type of cholesterol for the sterols. And by this method 50% of the vegetable oils can be detected in ghee microscopic examination. Now some of methods are which are there also based on the tracer components. Tracer components are those compounds which are present in the marker, that is the tracer compounds which are present in this very small quantity in the adulterant but not present in the pure fat. So for example, in sesame oil is there. So in India we have, it is mandated 25% sesame oil in vanaspati to enable its detection in ghee. And this video also is there in our this YouTube video. You can just quickly watch it. So this principle is that ghee plus with plus HCl will gives a pink color. And then in this sesame oil adulteration, that 5% sesame oil is to be added in vanaspati to enable this detection in ghee. And in this we know that sesame oil is having one component sesamoline, and sesamoline again hydrolyzed by HCl to sesamol which reacts with the purple to have the pink color. So if pink color is there at the bottom, then we would say that the milk is adulterated with the vanaspati. Ghee is adulterated with the vanaspati. So this is the Bowden test. The name of this test is the Bowden test. Okay, then another test which is based on tracer component. So tracer is again already told you that is not present in the pure fat, but is present the adulterant which we are targeting to detect. So tannins is there in the palm oil, which is present in impurity, which gives Persian blue color with the potassium ferricyanide or ferric and ferric chloride. So if the refining of the palm oil is not proper, then tannins will be there in the palm oil, and then these tannins will produce the Persian blue color with the potassium ferricyanide and the ferric chloride. And then its limitation is that if BHA is added, although now BHA has not been permitted to be added in ghee, but if it is present, then it also gives the positive test. Okay, so this is another test to detect the palm oil in ghee based on the impurity, that which is tannin. And if anyhow tannin is there in the palm oil, that will react with the potassium ferricyanide and the ferric chloride to give the Persian blue color. And if BSA is present, then that also will give the positive test. This is the limitation. So now in this video we will learn about the iodine value. So iodine value is also adulteration parameter. Now this parameter has also been included recently in the FSSAI standard. So let us see what is the meaning. What to mean by iodine value? Iodine value is expressed with the grams of iodine absorbed per 100 gram of lipid. This is the definition of iodine value. That is the grams of iodine that is absorbed by 100 gram of lipid or fat. That is known as the iodine value. Now the practical video of for this parameter is already there in this channel. So you can first watch it, and then you can learn about the theory. Now it gives the measure of degree of unsaturation of a lipid. So how much unsaturation is there, that indication is given by this iodine value. The higher the iodine value, the greater the number of CC double bonds. So if there is a more iodine value we are getting for any sample, so for example vegetables, we will have more iodine value. So this means that they are having more of the CC double bonds. Now one of the most commonly used method for determination of iodine value is the Vij method, and that is we are making use of Vij reagent in this. And Vij reagent is nothing but the this is iodine monochloride solution in acetic acid. Iodine monochloride in acetic acid is nothing but the Vij solution. So we make use of Vij solution in this test. The excess of iodine molecule is treated with potassium iodide. So what we are doing, we are treating excess of iodine molecule with potassium iodide, and the liberated iodine is then estimated by titration with sodium thiosulfate solution using starch as indicator. Okay, so this we will see in reactions also. So let us first discuss the procedure. What you have to do, you have to weigh 0.4 to 0.45 gram of the milk fat into 500 ml conical flask, earthenware flask with glass topper. There will be glass topper also, to which 15 ml of carbon tetrachloride has been added. Mix the contents well. So we are making use of 15 ml of carbon tetrachloride. Carbon tetrachloride is acting as solvent to dissolve the ghee. Then we will add 25 ml of the Vij solution using Brate and replace the glass topper. So we will then add the 25 ml of Vij solution with the Brate. We can use the measuring cylinder also. If you see in the video, we will have used the measuring cylinder. 25 ml of the Vij solution we will add, and then replace the glass topper. Then so the proper mixing motion we will properly mix it, and then we will keep the flask in dark for 1 hour to complete the reaction. Okay, now after standing, you have to 1 hour will complete in the dark. Take out the flask, and then you add 820 ml of potassium iodide solution, followed by 150 ml of recently boiled and cooled water, rinsing in the stopper also. So then you will add 150 ml of recently boiled and cooled water. So this potassium iodide will release the iodine. Then the liberated iodine, then you will titrate it with standardized sodium thiosulfate. So you have to ensure that sodium thiosulfate is properly standardized, that we are doing with potassium dichromate. That we are standardizing the sodium thiosulfate with potassium dichromate. Okay, then using starch as indicator at the end until the blue color formed disappears after shaking with the stopper on. Then you connect the blank determination also. So here in this blank determination is very important, because blank will have the higher value in this case and the sample will have the lower value. So the in formula also blank minus sample is to be done. So sample value is to be extracted from the blank value. So slight variations in temperature appreciably affect the titer of the iodine solution, as chloroform has a high coefficient of expansion. It is necessary the blank and determination, and we have to do both blank and the sample determination simultaneously. It's not that you are measuring the blank at some other time and you are taking that blank value for calculation of iodine value for any other sample. No. So you have to take the sample and the blank together simultaneously, so to obtain to arrive at the result. Now this is the reactions which are showing the principle. So this is unsaturated fatty acid. You will add excess of the iodine monochloride. So some of the iodine monochloride will react with the double saturated bond, and the remaining iodine chloride will be as such. And this remaining iodine chloride, when excess of potassium iodide will be added, you will, the iodine will release, and this iodine is titrated with sodium thiosulfate using starch as indicator. And we will see that at the end blue color will change to colorless as shown in this picture, and we will have some rose petals, like it seems that the rose color will be there at the bottom. So rose petal like which will appear at the bottom. So this way, otherwise at the top it will be colorless, and this will be the end point, and whatever titer value will you getting. So for blank it will be higher, and then for sample it will be lower, and then into normality which you have taken 0.1, and then weight of the sample which is taken, so 0.4 to 0.45 gram. Now here 126.1. So this is coming from the molecular weight of iodine. So if you should want to drive it, N1 V1 equal to N2 V2, and here V1 will go down. So normality of the iodine here we are taking, so we can apply, we know that normality is WB by MB into 1000 by V. In 100 gram we are taking, so V equal to N2 will be like this, V2 divided by V1 is nothing we have taken in weight, so it will be W. So normality here as such volume has come. Now molecular weight of iodine is, which we are taking, this 126.9, and then here we are volume we are taking per 100 gram, so here it will be 100. So this will be 12.69, it will go here, so it will be 12.69, and then weight B, that is in the grams of iodine will be there. So grams of iodine per 100 gram of fat will be calculated as 12.69 into N2 V2 divided by W. So this way this formula has come. So the 12.69 is coming from the molecular weight of iodine, which is 126.9. Okay. And we know that iodine value for Ghee sample given by PSI standard is ranging from 25 to 38. So if higher or lower value you are getting for Ghee sample, this means that the sample has been adulterated. So this way these are all the theory about. So here once more I would like to tell you, so what is happening exactly. So if for blank, since blank with this unsaturated fatty acid won't be there, so all excess we will be titrating with the sodium thiosulfate. All excess we will titrating with the sodium thiosulfate, but for sample some will be reacted with the sample, that is unsaturated bonds, and the remaining will be there. So for sample remaining we are calculating using sodium thiosulfate. So if we subtract the blank the sample from the blank, we will be able to know how much that the sample has been reacted with. Okay, so we want to know the iodine molecule which have been reacted with the unsaturated bonds, and this way we will be able to calculate the grams of iodine present in 100 grams of the sample. Okay, now let us see about the saponification value. So saponification value is also a parameter which is given by PSI. It's also a adulteration parameter, detection parameter, and the saponification value is defined as the number of milligrams of KOH required to saponify 1 gram of fat. number of milligrams of KH required to sponify 1 gram of fat is known as sponification value. So what do you mean by sponification? So this is a triglyceride molecule. When triglyceride molecule reacts with any alkali, say sodium hydroxide or hydroxide, this can be KH also. Then we will have the glycerol and the sodium or potassium salt of the corresponding fatty acids, and these are called the soap, and then this reaction is known as sponification. So soap are the sodium or potassium salts of the long chain fatty acids, these are known as the soap. And what is sponification reaction? So when alkali is allowed to react with triglyceride, we will have the glycerol and the sodium or potassium salt of the fatty acid, and this reaction is known as sponification. This reaction is known as sponification. So sponification value is defined as the number of milligrams of KH required to sponify 1 gram of fat, and it is an indication of average molecular weight of the fatty acid, and hence the chain length of the fatty acid present in the whole source fat. So it gives the average molecular weight of the fatty acid. Say in ghee sample we have more of the short chain fatty acid, so in 1 gram we will have more number of the such type of fatty acid, and therefore the sponification value of ghee is higher. Whereas if vegetable is all is there or animal fat is there, in that case long chain fatty acid will be higher, and since the long chain fatty acid will be higher, 1 gram of fat will have the lower number of these fatty acids, and hence the lower sponification value. So this is the significance. So it gives the average molecular weight of the fatty acid which is present in the sample. Now what are the reagents required? We have to have the alcoholic KOH. So we need approximately 0.5 normal in 95% ethyl alcohol we have to prepare. For that you dissolve 35 to 50 gram of the potassium hydroxide pellets in alcohol, or if necessary minimum quantity of water, and then dilute it with ethyl alcohol with 1 to 1 liter. The strength should not be less than 0.5 normal, and it should be colorless, and it should be kept in a dark place. Now for ethyl indicator, as we know that 1% solution is always prepared 95% ethanol, and HCl 0.5 normal aqueous solution that should be accurately standardized. So we can use the sodium carbonate to standardize the HCl. Now what is the procedure? So you have to take 2 gram of the sample in a round fat bottom flask, and then you have to 25 ml of the 0.5 normal alcoholic KOH solution, and then the contents were refluxed in a water bath for about 1 hour. You have to reflux the content in a water bath for about 1 hour. Then at the end of sponification, the contents were titrated with 0.5 normal HCl, and when it is hot, and using the phenolphthalein as indicator. So you will titrate using phenolphthalein as indicator. Okay, and blank test is very important, carried out using the same quantity of the KOH under the similar conditions, and the sponification value can be calculated as 28.05 T2 minus T1 upon W. So T2 is for the blank. We can write blank minus sample to remember it, blank minus sample, and this 28.05 where it is coming. So here the molecular weight of KOH, if you see there 56.1, and then from the formula N1V1 equal to N2V2, or N1 equal to N2 V2 divided by V1, since we have taken in W, so we will take here in W. So N1 is the normality of KOH, so WV by MB is 56.1 into 1000 by, so milligram per 100 gram. So we have to milligram of KOH so here milligram of KOH required to 1 gram of fat. So here gram we will take the 1000, so here it will be 1000 only. So it will go, and then we will have here as N2V2 divided by W. Okay, now W is equal to, that is milligram per gram of fat is equal to how much? So it will be 56.1. The 1000 will go 1000 into normality is here 0.5. So here since normality is 0.5 into that is the V2 divided by W. So 0.5 into 56.1 is nothing but the 28.05. So this is how 28.05 is coming. So in some books if it is written that 56.1 into normality is also written, then it is okay. So blank minus sample divided by W. So this is the formula can be used, and if you put the value of normality here, this will become 28.05. So don't get confused. The formula is, this is okay, this is also correct. Okay. Now for blank, what is happening is that why blank means, so remember that we are subtracting the value sample the blank value. So and why this is happening, that I tell you that meanwhile there is a term sponification number, so 560,100 divided by sponification value, that give you the sponification number. Or you can also calculate the average molecular weight of fatty acid is equal to the 56100 upon my sponification value. So average molecular weight of acid in a sample is equal to 560,100 upon my sponification value. So for what is happening actually in the blank, so for when we are taking blank, so this triglyceride won't be there, so all the alkali which will be remaining in the sample, and that will be titrating with the 0.5 normal HCl. But if sample is present, then sponification will happen and some of the KOH will be used, and the remaining KOH will be here determined using the 0.5 normal aqueous saline. So if when blank, so we want to know how much is that reacted, note the remaining one. So here in this we are calculating the remaining one. When the sample is there, we are calculating the remaining one. So or total KOH which is there minus the remaining one will give you that KOH that has been used for the sponification. So that is why blank minus sample is coming here. So that is why blank minus sample is coming. One more thing, that you know that the FSA has given the standard for the sponification value of ghee is 205 to 235. So if the value is coming less, so because you know animal wood fat and if you are adding vegetable oil, animal wood fat in ghee, then the sponification value decreases. And if the sponification value is not in this range, then we will say that our ghee has been tempered.